Although matrix mechanics and wave mechanics have now been shown to be equivalent, Max Jammer remarks that it is hard to find in the history of physics two theories designed to cover the same range of experience which differ more radically than these two. Heisenberg's was a mathematical prescription involving non-commutative quantities and computation rules, which defied pictorial visualization, and, proceeding from the observed discreteness of spectral lines, emphasized the element of discreteness. Schrödinger's, in contrast, was based on the familiar apparatus of differential equations. Proceeding from a generalization of the classical laws of motion, it was a theory whose basic conception was the easily visualizable wave. These two theories did not initially find favor with the opposite camp. Heisenberg criticized Schrödinger's approach as not leading to a consistent wave theory. The more I ponder about the physical part of Schrödinger's theory, the more disgusting it appears to me. Schrödinger was equally critical of Heisenberg's approach. I was discouraged, if not repelled, by what appeared to me a rather difficult method of transcendental algebra defying any visualization. Adopting Dirac's picture, where any state is a vector in an abstract Hilbert space, its representation in a given orthonormal basis is written in terms of its expansion coefficients in those basis vectors. The state vector in the Ket space is represented by a column vector in that basis and its conjugate by a row vector in the Bra space. The important distinction is that a wave function is a vector in an abstract Hilbert space, the Ket space or the Bra space, while its representation in a chosen basis is given by the row or column vectors. Physical properties correspond to operators which are then represented by matrices in the same basis. Schrödinger interpreted psi star psi as the weight function of the charge distribution, so that E psi star psi is the electron charge density. From the time-dependent Schrödinger equation, H psi equals I H cross del psi by del t, with rho equals E psi star psi, we have del rho by del t equals E times psi star del psi by del t plus psi del psi star by del t, which is equal to E by I H cross psi star H psi minus psi H psi star, which is equal to minus E H cross by 2 Im times psi star del squared psi minus psi del squared psi star, where we have used the time independent form of the Schrödinger equation. H psi equals minus H cross squared by 2m del squared psi plus V psi. Defining the current density J as J equals E H cross by 2 Im times psi star del psi minus psi del psi star yields the continuity equation del rho by del t plus del dot j equals 0. However, the empirical fact is that the electronic charge is generally found to be concentrated in a very small region of space. While Max Born regarded Schrödinger's formulation as the most profound formulation of the quantum laws, he realized that every experiment by James Frank's group in his neighboring lab at Göttingen seemed to confirm the corpuscular nature of the electron. Born thus adopted Schrödinger's formulation to develop a quantum mechanical explanation for the process of collision between an electron and an atom. For the scattered wave at large distance from the scattering atom, Born obtained this formula, where d omega is an element of the solid angle in the direction alpha, beta, gamma, and the wave function psi nm e of alpha, beta, gamma determines the differential scattering cross-section in the direction alpha, beta, gamma. If this formula is to allow for a corpuscular explanation, then psi nm of E modulo squared has to measure the probability for the electron to be scattered in the direction alpha, beta, gamma. Hence, Born concluded Wave mechanics does not answer the question what precisely is the state after the collision, but rather the question what is the probability of a definite state after the collision. In his words, the motion of particles conforms to the laws of probability, but the probability itself is propagated in accordance with the law of causality, as he wrote in his paper Quantenmechanik der Stoßvorgänge in the Zeitschrift für Physik 1926. Laws of nature determine not the occurrence of an event, but the probability of occurrence. Since the wave function psi can be expanded in terms of a complete orthonormal set of eigenfunctions, that is psi equals sigma n Cn psi n of the Schrödinger equation, integrating the square modulus of the wave function over all values of the coordinates gives integral psi of q modulus squared dq is equal to sigma n Cn modulus squared. Born also computed the expectation value of the energy E for the state psi as E equal to sigma n Cn modulus squared times En, and concluded that Cn modulus squared is to be interpreted as the statistical frequency of occurrence of the state psi n. This brings us to the postulates of quantum mechanics. The first postulate is that the wave function psi of a system determines all its measurable properties. And as we have seen, psi star psi is interpreted as a probability. The second postulate is that every observable can be characterized in quantum mechanics by a linear operator whose expectation value gives the average value of this observable. The third postulate of quantum mechanics is that for a system whose total energy does not vary with time, we call this a conservative system, the wave function satisfies the time-independent Schrödinger equation, that is h psi equals E psi, where h is the Hamiltonian operator whose eigenvalue gives the total energy E, which is a constant independent of time. More generally, the Hamiltonian satisfies the time-dependent Schrödinger equation h psi equals IH cross del psi by del t, where h cross is Planck's constant divided by 2 pi. This is the fourth postulate of quantum mechanics. Combining this with the time-independent Schrödinger equation h psi equals E psi for a conservative system, we get h psi equals E psi equals IH cross del psi by del t. This as the general solution, psi at the time t is equal to psi at the time 0 times e to the power minus IET by h cross. To obtain the solution of the time-dependent Schrödinger equation for a conservative system, that is h psi equals IH cross d psi by dt, and for a conservative system we know h psi equals E psi. So IH cross d psi by dt is equal to E psi, or d psi by psi is equal to minus IE by h cross times dt. Integrating both sides, we get integral d psi by psi equals minus IE by h cross integral dt, or logarithm of psi is equal to minus IET by h cross plus the constant of integration, or taking anti-logs on both sides, we get psi is equal to constant times e to the power minus IET by h cross. Now at time t equals 0, the left hand side can be written as psi at time 0, and the right hand side is equal to constant because the exponential just becomes equal to 1 at t equal to 0. Therefore, we get the constant is equal to psi of 0, and therefore psi of t is equal to psi of 0 times e to the power minus IET by h cross. Let us solve the wave equation for a plane wave in one dimension, which can be written as psi equals a cos kx plus b sin kx putting b equals ia, this can also be written as psi equals a e to the power ikx. We see that this is an eigenfunction of the operator minus IH cross d dx, since minus IH cross d psi by dx is equal to minus IH cross a times d dx of e to the power ikx, which is equal to h cross k a times e to the power ikx, which is equal to h cross k psi. Thus, the eigenvalue of the linear momentum operator is px equal to h cross k. This is the de Broglie relation, since k is the wave vector which has the dimensions of inverse length. H cross, of course, is Planck's constant by 2 pi. We see that the linear momentum operator px, which is equal to minus ih cross d dx, does not commute with the position operator x. To evaluate this, we operate with the commutator upon the wave function, that is commutator of px and x operating on psi equals px x psi minus x px psi, which is equal to minus ih cross dx of x psi plus ih cross x times d psi by dx. Differentiating the first term by parts, we get this is equal to minus ih cross psi times dx by dx minus ih cross x times d psi by dx plus ih cross x times d psi by dx. The last two terms cancel out to give minus ih cross psi dx by dx, which is equal to minus ih cross psi, which is not equal to 0. Thus, the commutator of px and x is equal to minus ih cross, which is not equal to 0. Therefore, there is no state psi that can be simultaneously an eigenfunction of both the linear momentum px and the position x. In other words, the position x and the linear momentum px cannot be simultaneously well defined. This is Heisenberg's uncertainty relation. Similar uncertainty relations hold for any pair of non-commuting operators. Thus, for the other components of linear momentum, we have commutator of py and y equal to minus ih cross, which is not equal to 0. Commutator of pz and z is equal to minus ih cross, which is not equal to 0. However, operators that commute can have simultaneously well-defined eigenvalues. We can show that the commutator of px and py equal to 0, the commutator of px and pz equal to 0, the commutator of py and pz equal to 0, and also the commutator of px with p squared, the square of the total linear momentum, is equal to 0, commutator of py with p squared equal to 0, commutator of pz with p squared equal to 0. Thus, all of the components of linear momentum as well as the total linear momentum can be simultaneously well defined. The mathematical foundations of quantum mechanics were well established by 1927 or so, namely Heisenberg's matrix mechanics, Schrödinger's wave equation, Dirac's commutator algebra, and so forth. But there continued to be vigorous debate about the philosophical implications and the interpretations of quantum mechanics for several decades. The probabilistic interpretation of the wave function introduced by Max Born and the complementarity principle championed by Niels Bohr were two of the main pillars of what is known as the Copenhagen interpretation of quantum mechanics. As I have mentioned already, Born and Einstein carried out a lifelong correspondence, and Born greatly valued Einstein's friendship and sought his approval, especially for the probabilistic interpretation of the wave function. But much to Born's disappointment, Einstein continued to resist, and the probabilistic interpretation of the wave function was anathema to Einstein all his life. Okay. We will return to these philosophical questions and the associated debates in a later episode. But in the next episode, we will delve into the nitty-gritty of quantum mechanics and use the mathematical apparatus that we have just developed in order to clarify the origins of quantization. See you then.